Modern workloads evolve quickly, and so do their storage needs. Over time, block storage volume originally provisioned for a peak data load may end up significantly underutilized. And continuing with oversized volumes not only waste resources but also increases cost without delivering added value. Hello everyone, I'm Sanskriti Harmak, a developer relations at Vultr, and in today's Tech Talk, we will walk through how to safely shrink and later expand your Vultr block storage volumes to reflect its actual usage. Since Vultr Block Storage is persistent and also supports on-demand attachment and detachment from instances, it is well suited for dynamic workloads and long-term storage alike. So, without any further ado, let's explore how to optimize your storage footprint without compromising data integrity or application uptime. Vultr Block Storage is a persistent storage solution that let you attach high performance volume to any instance across supported regions. These volumes come in two flavors: standard backed by HDD and high performance backed by NVMe SSD. These are fully encrypted using AES 256 algorithm. Each volume is presented as a virtual block device, meaning you can format it with any file system, mount it anywhere in your instance's directory tree, and manage it independently from your compute lifecycle. This decoupling is especially useful for workloads that require flexible capacity, high IOPS, or reliable backups. Since volumes can be resized, detached, and reattached at will, Vultr Block Storage serve as a foundational tool for scaling applications, managing logs, hosting databases, and more. Shrinking block storage is more than just a cost-saving step. It is a proactive way to optimize your cloud architecture after log rotation, database pruning, or archival. By reducing the storage footprint, you directly lower your monthly storage cost while also improving backup speeds and data migration times. Smaller volume typically results in faster I/O operations, especially when fewer blocks are accessed and indexed during runtime. It also simplifies snapshot management since less data means quicker differential backups and easier replication. All of this translates into more agile and more efficient cloud environment. Expanding storage is comparatively more straightforward and much more common. It gives your infrastructure the flexibility to keep pace with data growth, whether that is driven by increasing user traffic, expanding datasets, or more intensive application workloads. For example, growing a volume can help scale relational and NoSQL databases, media servers, or log directories without needing to provision new instances or re-architect your deployment. This reduces downtime caused by running out of disk space and avoids emergency interventions that could disrupt service. With Vultr Block Storage, you can resize volumes on demand and retain all your existing data and mount points, ensuring seamless continuity for applications and services even if storage requirements evolve. Next, to see it all in action, let's dive into a hands-on demo. We'll start by analyzing the current block device layout to identify unused partitions or a space. Once we confirm there is room to downsize, we'll provision a new Vultr Block Storage volume with a smaller size. This new volume will serve as a target for safely migrating data. We'll first mount the smaller block storage volume to the instance, copy the data from larger block storage volume to the smaller block storage volume, and then finally detach the larger block storage volume from the instance. Finally, we'll demonstrate how to expand the new volume to accommodate future growth. Throughout the process, we'll ensure that the data remains intact and instance continues running without interruption. To set the environment, we are working with Vultr Cloud Compute instance running Ubuntu 24.04 deployed in the New Jersey region. Attached to this instance is the 15 GB NVMe Vultr block storage volume, also provisioned in the same region as that of our instance. Now, let's access our instance remotely to inspect a few things before we move on to the shrinking process. We'll start by analyzing the current storage layout using LSBLK. It lists all available block devices and their mount points. As you can see, our large block storage volume is also mounted here. Now, let's list the content of this mount point to inspect how much data it holds. There is approximately 2 GB of data on this volume. Since the attached volume size is much larger than the data it holds, it is clearly underutilized. To optimize the storage and cost, we will migrate this data into a smaller volume. For that, let's head to the Vultr customer portal and provision a new Vultr Block Storage volume. From the product section on the Vultr customer portal, navigate to the cloud storage and then to block storage, and here click on add block storage. You will be prompted to choose from two available performance tiers. For this demo, we'll go with NVMe block storage as it offers lower latency and higher throughput for performance sensitive workloads. But if performance is not a priority and you are just looking to minimize storage cost, then you can opt for HDD block storage. It also offers affordable persistent storage and is globally available. Next, make sure to choose the same region as the instance. In this case, we'll go with New Jersey. Further, set the volume size to 5 GB as this will be sufficient for the 2 GB data that we plan to migrate. And then provide a label to your Vultr block storage volume for easy identification. Finally, once everything is configured, click on Add Block Storage. Now that our volume is active, let's click on it to open its management page and attach it to our instance. Next, let's switch back to our workstation to mount this newly provisioned Vultr Block Storage volume. Although the volume is already attached at the infrastructure level, it still needs to be formatted with a file system and mounted at a directory path before it can be used by the operating system. If you're using Windows or FreeBSD, we have dedicated documentation to guide you through the mounting process on these platforms. Please find the link for the same in the description below. Before we begin, let's confirm our new volume is recognized by the system using LSBLK. This shows all the available block devices, including our new volume VDC, which currently has no partitions. Next, we'll create a GPT partition table on dev VDC. GPT is a modern standard and is required by disk larger than 2 TB, but it's also a safe choice for smaller volumes. Now we'll create a primary partition that spans the entire volume. We use unit megabyte to ensure precise alignment for performance. With the partition created as devvdc1, we'll now format it with ext4 file system, which is reliable and widely supported on Linux. Next, we create a mount point directory. This is where we will attach the volume in our file system hierarchy. Now let's fetch the UUID of the new partition. We'll use this in the fstab file for persistent mounting across reboots. Using the UUID we just fetched, we'll now update the fstab file. This ensures that our volume automatically mounts at mount a small block storage after each reboot. Let's reload the systemd daemon to apply the changes we just made to fstab. Now, let's finally mount the volume for immediate access. It is now time that we run LSBLK again to verify that the new volume is now mounted and is visible with its mount point. The newly provisioned Vultr block storage volume is now mounted successfully, so we are ready to copy the data from larger volume to smaller one. We will use Linux specific command since our instance is running Ubuntu 24.04. But if you're working with Windows or FreeBSD, the steps and tools required will differ. We have outlined the appropriate workflows for those operating system in our How to Shrink Vultr Block Storage volume guide. You can find the link to that documentation in the description below. To migrate data from larger volume to the new smaller one, we will be using rsync utility. It's a reliable tool for efficiently copying files and preserving metadata such as permissions, timestamps, and symbolic links. We will also be explicitly excluding lost plus found directory, which is automatically created on a newly formatted ext4 file system and is not relevant to our data. The A flag in this command enables archive mode for preserving file attributes. V enables verbose output, and C tells rsync to perform checksum based comparison instead of relying on file modification times. After the copy completes, we can run the dry run command to confirm that all files were transferred. As no file names appear between the header sending incremental file list and the final summary, it indicates successful and complete transfer. Once the data transfer completes, let's verify the content on the smaller volume to ensure that everything has been copied successfully. You should see the same set of files and directories that existed in the large block storage mount. Now that we have verified the data, we can safely unmount large block storage volume. Let's run lsblk to confirm the mount. The large volume will still be listed by a device name VDB, but should no longer show a mount point. At this stage, it is important to update the fstab configuration to avoid mount errors on reboot. For that, Open the file using your preferred text editor. Locate the line that references large block storage mount and delete it. This ensures that the system doesn't try to mount a now unused volume automatically during boot, which could otherwise result in a delay or failure. Now let's head back to the Vultr customer portal to detach the large block storage volume from our instance. Since we have already migrated the data and removed its mount configuration, it's safe to detach this volume. With that, the shrinking process is complete. Let's now walk through how to expand a Vultr block storage volume. This can be useful if your storage needs grow over time. To see this in action, open the management page of a small block storage volume. Click on its current size to enter the edit mode. Vultr requires the expansion to be greater than 5 GB than the current size. So we will increase it from 5 GB to 12 GB. To proceed, type yes in the confirmation box and then click on continue. This operation resizes the volume at the infrastructure level, and a similar result is also achievable programmatically using Vultr API or from the comfort of your terminal using Vultr CLI commands. Let's now detach and reattach the volume to our instance. This ensures that the operating system recognizes the updated size of the volume at the hardware level. After reattaching the volume, we will reboot the instance to reload the block device mappings. After rebooting the instance, you'll notice that the mount point persists. That is because we previously configured fstab, so Linux automatically remounted the volume at boot. You'll also see that the device name previously labeled as VDC is now VDB. This reassignment happened because we detached large block storage volume, which was earlier assigned as VDB. Linux dynamically reorders device names based on attachment sequence during boot. The block device now shows the updated size, which is 12 GB in our case. However, the partition inside it still reflects the old 5 GB size. So while the block size has been resized, the partition hasn't yet been expanded to utilize the extra space. To fix that, we'll use the interactive parted utility to resize the partition. At the parted prompt, enter print. This may trigger a warning because the GPT partition table hasn't been updated yet to reflect the new disk size. Type fix and hit enter. Then let's resize partition 1 to occupy all the available space. Type yes when prompted and enter quit to exit from the interactive interface. With the partition layout updated, the final step is to grow the file system itself to match the new partition size. But first, let's run a consistency check using E2FS check to make sure that the file system is healthy. Once that completes, expand the file system. For one final round, let's recheck the block layout using lsblk. You should now see that the entire 12 GB is now available to the mounted directory. If you want, you can separate the resized volume into multiple partitions instead of using the entire disk for a single one. This can be useful for organizing data, applying different mount options, or isolating workloads. And in that way, we have completed the entire workflow from shrinking a larger Vultr block storage volume down to a smaller one to expanding it again when needed without data loss or downtime. To summarize, Vultr block storage gives you complete control over your persistent storage lifecycle. With support for both expanding and shrinking volumes, you can right-size your infrastructure dynamically, cutting cost, improving I/O, and maintaining the storage hygiene. If you're ready to try this yourself, then get started today on Vultr with $250 in free credits on a new account using the promo link attached in the description below. And if you have any questions or just want to see how others are using Vultr block storage in production, then join the conversation on the Vultr community forum. Thank you so much for tuning in. We hope this tech talk helps you manage your storage more efficiently.